Hi, in this video we will be discussing section 3 of chapter 3. We'll be talking about coordinate systems and vector components. So, coordinate systems. What is a coordinate system? A coordinate system is some artificially imposed grid that we're going to use to place onto a problem to help us describe and analyze a physical system. Since this is an artificial imposition we're making on the problem, you're free to choose where you will place your origin of your coordinate system and also how to orient the axes of your coordinate system. Notice that for a two-dimensional coordinate system that we'll frequently use in the course here, that the two different axes are oriented 90 degrees with respect to one another. This is a conventional XY coordinate system with 4 independent quadrants numbered 1 through 4. By convention, angles in this sort of coordinate system are typically measured from the x-axis, moving with positive angles going in the counterclockwise direction. Once we've defined a coordinate system, we can then use this to help us describe a vector quantity that we're observing in that coordinate system. The figure shows in this example vector A placed on top of an XY coordinate system that we've chosen. Remember, this was a free choice. We could have put the origin of this coordinate system anywhere we like. We could have placed it at the tail of this vector, or we could have placed it far away. We could also have rotated the y and x axis in this example. That was a free choice we get to make when we define our coordinate system. And as we go along in course and you practice problem solving, we'll find that all choices of coordinate systems should result in the same physical answers for a given problem, but some coordinate systems, choices of coordinate systems may make the problem simpler to solve, and we'll practice with identifying those coordinate systems. Once we have that coordinate system, that xy coordinate system defined, we can then define two new vectors. We're going to define vectors that are parallel to each of our axes, one parallel to the y-axis, one parallel to the x-axis, such that when we add those two vectors together, they give us vector A. Those resulting vectors we're going to call the component vectors. Okay? So for instance here, we're going to find two vectors, vector ax and vector ay, such that when I add them together, they give me that vector A that I've placed in my coordinate system. Vector ax, we can see here, is parallel to the x vector. Vector ay is parallel to the y-axis. And you can see that when I put them tip to tail, ax plus ay, I'll get this vector, this total vector A, right? The original vector. You can see vector ax is just the, right, you could imagine projecting vector A, right? It's what you might imagine if you could sort of visualize shining a light from above vector A. It's the shadow or the projection of that vector down onto the x-axis. If I had a source of light, say, coming from this direction, creating a shadow down onto the y-axis, vector A would, that's the result that I would get for vector ay here. The y component is parallel to the y-axis. The x component is parallel to the x-axis. Why is this nice? Because this breaks that vector A into two perpendicular vectors that are parallel to the coordinate systems. Okay. This is called vector decomposition, and we're going to use this idea over and over again as we go throughout the course. Any vector that we place into a coordinate system can be decomposed into these two component vectors. Or if we have higher dimensions, if we have a three-dimensional coordinate system, it could be broken down into 3 individual vector components. Okay, so suppose we have vector A and it's been decomposed into its vector components, ax and ay, parallel to the coordinate axis. Well, then we can describe each component with a single number that we're going to call the component. Okay. Each component vector can be described by a single number. The component tells us how big the component vector is in that particular direction. And we're going to use the sign that's going to tell us the direction that that vector points. Let's look at these two examples to the right to see what we mean here. Here's vector A. We can decompose it into AY and AX, our two component vectors. AY points in the positive y direction, and so we can say that AY is equal to plus 2 meters. This plus sign indicates that the vector points towards increasing values of y, and so this describes this vector component. AY is equal to plus 2 meters means I have an upwards pointing vector component parallel to y. What about AX here? You can see again it points in the direction of increasing values of x in this coordinate system, so it's going to have a positive value associated with it. So AX is equal to plus 3 meters. Compare that to vector B here. Now when I decompose this vector into its vector components, BY points in the positive direction and is 2 units of 2 meters, right, is 2 meters long. And so I can say BY, that component vector, is equal to plus 2 meters, whereas BX now points towards decreasing values of x, so I'm going to use this minus sign to indicate that the direction of that vector, right? It's 2 meters in length, but the minus sign tells me that vector BX points to the left. Okay. So when I'm writing these vector components in this notation, positive sign means that vector points in the direction of increasing value in my coordinate system. Negative sign means it points in the direction of decreasing values in my coordinate system. Okay. So how do we determine components of a vector? The absolute value of some vector components, say AX, is the magnitude of that component vector. The sign of that AX, right, of that vector component, is positive if A points in the positive x direction, right, and negative if it points in the negative direction. A similar trend holds in the y direction. So now we see that we have several different ways of representing vector quantities. We can just draw a vector and have a geometric representation, right? This arrow that we put on the page that has a direction and a size. But we can also draw a coordinate system and describe that vector in terms of the vector components AX and AY. Another way we could describe that is with a geometric representation where we describe, right, that we've seen before, where we just describe the magnitude of vector A and some angle with respect to some direction here. How does that all work together here? Okay. Let's look at this example. Here's vector A that we've placed in an XY coordinate system. The magnitude and direction of A are found from the components, right? I can find vector AX. It's going to be this vector that, right, spans the length of vector A. It's going to point in the positive x direction. Vector AY, right, AY is going to be a positive value. It's going to point this direction. What are the magnitudes of those? Well, let me define this angle theta that is running counterclockwise from my positive x direction. Then I can see AX is just going to be A cosine theta. Remember what cosine of theta is. It's the opposite over the hypotenuse. If I divide A over here, I just get that AX over A has got to be equal to cosine theta. So AX is just A cosine theta. AY is equal to A sine theta. Remember, sine is just the opposite over the hypotenuse, whereas cosine was the adjacent side over the hypotenuse. So I have all the different representations shown on this plot. I have the graphical representation, the green arrow here. I could describe that as a vector that has a magnitude that's equal to the square root of AX squared plus AY squared, right? Just the Pythagorean theorem. That some angle above, right, or counterclockwise from my x direction. That angle has got to be related to the tangent of my angle theta, which has just got to be AY over AX. Remember, tangent of theta is just my opposite side over my adjacent side in my right triangle here. And I also have the vector components here. I know those vector components are just A cosine theta. AY is just A sine theta. If we have a vector, a component vector that points to the left or down, you remember you must manually insert that sign in front of the component, as is done in this example for BY. Okay. The role of sines and cosines can be reversed depending on which angle you're using. So be careful when you're to not just blindly say that AY is always associated with a cosine of the vector. It depends on the definition of the angle you're using. The angle used to define the direction is almost always the acute angle, right? Something between 0 and 90 degrees. So let's look at this example. Here I have the graphical representation of B. I've defined an XY coordinate system that I've placed that vector in. Here I can see that there's a Y component of that vector B. I'm going to put a negative sign in there because I can see that that component would have to point downwards towards decreasing values of y. If this is my reference angle that I'm using, I'm going to use this angle that goes from the y-axis and rotates counterclockwise. Well, then I know that I want this adjacent side to that angle, right? So the adjacent side over the hypotenuse would be cosine of theta here. So cosine of theta times my hypotenuse, my vector b, would give me by in this example. What about bx? Well, now bx is going to be the vector that's the opposite side of the right triangle from this reference angle theta, and so bx is going to be b sine theta. The minus sign is manually inserted. Remember, this trigonometry we're doing here is just for a right triangle, which doesn't know anything about the directionality, so you have to manually insert that you know that that vector b y has to point downwards in this case, so that when I add by plus bx, I get this resulting vector b that points in the correct direction. Okay, that concludes our discussion of section 3. Thank you for your attention.